Hi, welcome today. In today's session, we'll be diving into the introduction of artificial neural network, or AI as we commonly call it today. We've seen from the news, at work, at home, how much ChatGPT like application, I don't know, maybe you are a cloud code person, whatever flavor of AI chatbot you use today, it's part of our life. And fortunately, or for some, unfortunately, depending on how you look at it, it's here to stay for the long run. So it's very important to get the foundation, the basic of what make AI work. So down to the low level, how do you get the intuition on today's AI advanced features, what make AI work today? We will be going through a simple example, and I can tell you right now, we'll be learning addition. Here, interesting. If I ask you 1 plus 3, you don't need to think a lot, or you don't need to be expert in math to know the answer to that question. If I give you 0 plus 2, you know right away the answer to that question. Now, it obvious for us, of course, it's obvious for computer. We do have, calculators at home, or when you were at school. So you basically know that this is a solved problem. But the interesting fact of this example is that it's a simple enough example where we know the answer, and we can try to make the computer dumb enough to forget addition and to rediscover the rules as a child of what it means to add two numbers together. So that's what we'll be exploring today. And stick with me, I will not be introducing any mathematical concept that we don't need for this introduction. Think of this as your hello world into AI. First, you will understand what AI need to work. You will learn how AI work, how AI learn, and finally, you will be training your own AI. That's exciting. And that AI, you will test it on something that you as an expert, addition expert in this case, you know the answer to all the questions, and see how can you teach the computer to rediscover the rule of addition. So let's get started today. So the introduction for this session, I will be talking about traditionally what make traditional programming different from AI. Then I will talk about how does AI learn. I will create the training data. As you understand, AI need data to learn from. And then we will initialize the model, show you how the model look like, train that model, and finally run inference on that model. So let's start with how does traditional AI compare to traditional programming compared to AI. In traditional programming, you have two information. You have the rules and the input. And you are given a program, or you write a program that is able to do the input to output mapping. So if I give you two numbers, you might be a calculator, you might be a Jupyter notebook, whatever you are, you might be just, a Python code. If I give you x1 and x2, I don't want you to think a lot. Just give me the result, which is equal to x1 plus x2. So we wrote down the rule for the computer, and it's just returning us that result. And this is an example in Python. This applies in Java if you are a Java person. So Java is another programming language, so the way humans talk to computers. So if you are a Java person, you give it also x1 and x2. It's the same thing happening behind the scenes. So it will just take a variable that will be storing x1 plus x2 and returning that value to you. So basically, traditional programming or classical programming, you have on one hand the rule that you want the computer to do, and you have input that you want those rules to be applied on. And what you get as output is your sum. In this case, the result variable is being returned to you. So how does this contrast? So first, there's no notion of probability in this case. If you give it 10 plus 2, you got 12, 22 plus 11, you got 33. So you don't need to think twice. You just give it number, it's giving you the exact answer. So that's very important distinction here. But in machine learning, or the concept we'll be introducing to the neural network or AI, you are given, in this case, input and output. Notice the distinction here for a minute. You do not know the rule. This is an interesting stop here. Think about the task of training a model to detect a cat versus a dog. If I ask you on the classical programming, can you please think hard and write for me a program where I give you a pixel of images and I want you to tell me if the given image is of my cat or my dog, if not just mine, my neighbor's cat or my neighbor dog, actually any cat in the world or any dog in the world. So if you're a programmer here, you can take a minute to think about it. What kind of variable do you need for that? If you just have like the raw pixel, it's not a straightforward code that you need to design, because you need to think about how different breed of dog look like, how different kind of cats look like, and how do you really code the difference between dogs manually? How do you exactly give explicit rule on the computer to carefully tag all the cat versus dogs? You might be successful after thinking for a long time, and of course your code will be very long because you need to take into account all the aspects that make cat different from dog. But the difference with AI and the concept I will be introducing here today is that when you do machine learning, you don't need to know the rules. You just need two information, the input and the output. In this case, in the example illustration I was talking about, you just give me a picture of a cat and tell me that a cat. Give me that a picture of a dog, tell me that a dog. So my input is the image of the cat. My output is telling you that this is a dog. So basically, I can collect image from my friend, from my colleague, many dogs that I can get outside of it on the internet and give to the computer. This is as many dogs that I could find out there. This is as many cats that I could find out there. Can you now learn the rules? So you see where the difference lies. In this case, the computer will be deriving the rule based on the input output you've shown it. In this case, it's pretty straightforward with our addition example. Our input output mapping are pair of number and the sum. You will be giving 0 and 0 and telling computer I want you to predict this to be 0. Giving it 1 and 0 and you ask the computer to learn it as 1, and so on. So basically you need to give it as many examples as possible and hoping that the system can learn the function f of x1, x2. So basically we are learning the function f of x1, x2, so which is like the rule. So we want the rule, which we in this case we explain it as a function that is taking two input and mapping it to a single value. We don't care what might happen. Actually, we do care, but we want you to intelligently learn the mapping between f of x1 and x2 to a value y. In summary, this is the difference. Classical programming, you have rules and input, you learn output. But in machine learning, you have input, output, you learn the rules. Different paradigm, but same result. Okay? So, the dream of having a machine that can think as we humans do is not born with ChatGPT or with cloud code. Those dreams are very old. People have been thinking about how do we make computers or have automated systems that can think like us, that can be as intelligent, if not more than we are. So you can see here an example on what was the inspiration of what we call neural network. So when you hear about neural network out there, it's an approach to AI that tried to mimic biological neuron in human brain. So you can see from this image, neuron is made of different things like the soma, the axon, and so on. Someone with biology background will probably be able to explain this more than I. But basically, researchers have tried to map, can we build artificial component or mathematical function that can try to represent this biological component into math and allowing us to learn from data. So let's now return to the addition and see how do we get that function that we're trying to learn, because the gap here is that we have input output, we can pass input output to a function f, but how do we get the y? So this is with this formula, a very famous formula, where you basically been told that to get from a pair of number, this formula actually can be generalized. It doesn't need to be 2 numbers, it can be 1,000 numbers. So basically, if you have a function, you can think of it as having a multiplication of w1 plus your multiplied by your first input plus w2 multiplied by your second input plus w3 if you have as many w as possible. In this case, we just have 2 input, so that's why we stop here by w2 times x2, but we do add a bias. And why do we really need a bias? It's because this function is trying to learn the input output mapping. So if we don't have bias, what end up happening is that for the input pair of 0 and 0, we have deterministically fixed y. So basically, every prediction will map to 0 because we don't have any other independent variable that is changing regardless of our input output. So bias play a different role mathematically, but the intuition I want to leave you here with for you is to understand that the reason we have bias is to make sure that if for whatever reason our input is 0 out, we still have a value that is potentially non-zero. If we want the value to be 0, it's easy. We will make bias 0, then we have a 0 value for an input and a x1, x2 input of whatever value. But if for some reason we want for an input pair of 0, 0 to have a y of a non-zero value, the bias will be our free agent. It can be -1, it can be 50, it can be 1,000, because it's independent on our x1, x2. I hope this intuition is useful, but basically that's why the bias is playing a role in this case. So this formula, if you are interested, you can read this article here down here. I have the link and the DOI information for you to look it up. Yes, so now that we know which function, our mathematical formula that we can combine our x1 and x2 with in order to obtain our y prediction that we call here f of x1, x2, so which is basically the guess of our naive model to start when starting random. Unpack again the formula. So this is the formula that we just learn, is that to get a prediction or a guess of the addition given our input, in our case the input we'll be playing with throughout this demo here is x1 of 2 and x2 of 3. So remember that, we'll not change that. So we know that 2 plus 3 is equal to 5. But what happened here, initially we know the value of x1, which is 2, the value of x2, which is 3, but we don't know w1, w2, and b. So because these are parameters, and again, parameters are a set of numbers that are actually multiplying our input to give us our initial guess to the addition here. And a stop here, most of the time you hear from generative AI, like they have this number of parameters, which actually mean they have this number of w1, w2. It might have different nomenclature or different name, but basically those are things that you need to tweak to make your big network behave the way you want. So that's very important concept here. In our case, we start randomly. We could have started with any number. In this case, we start with number 0.14 for w1 and then minus 0.47 for w2, and we will start with a bias, which is that b of minus 0.22. So remember this value, you don't need to write it down, but just know that these are the value that we'll be using to start with our initial guess, and learn how do we change it to make it match our addition rule that we're trying to learn. So when applying this formula, you can clearly see that we are very far from what we expect the model to know. So we know that our y is 5, but so this is like we refer to this as our ground truth. So this is the value that we want the model to learn. So this is an example that we want the model, if given 2 and 3, it should output 5. But by applying the formula that we were just introduced to previously, it actually giving us minus 37, which is really far away from 5. But how do we quantify how far it is? So this is where the notion of error come to play. So how do you know how far the guess of the computer is from the value you want the computer to output? Is by finding mathematical way to compare the two values. In this case, the error, we quantify it as taking the prediction value minus the value that we wanted to have. So this will tell us a level of measurement, how far away or how close we are to the expected value. In this case, you will see that the value is giving us minus 6.37. So telling us that, okay, ideally, assume that we had a value of 5 as we expect it to be, you will see that our error is behaving as expected, then the value will be 0. So E will be like 5 minus 5, which is telling us that we actually have the right error. But there's one caveat here. This error might not be a good idea, specifically because as we work with many examples, like machine learning doesn't learn from just one example. So you need a bunch of examples, ideally thousands of them, that will give different kind of example to the computer so that it can learn different variation. And back to the example of cat and dog, you remember, you need to give different, kind of dog, and dog in different setup. It might be in the couch, it might be maybe playing outdoor. So you need different scenes so the model can learn how to generalize. So basically not memorizing what it has seen, but try to generalize in such a way that even if in the future it sees a dog in let's say in a driveway, or maybe a dog in a playground, it can still learn what make the dog different from every other things around in the background in the playground. So generalizability is a very important concept here. I don't know if the generalizability is a word. Is it? Oh, tell me if it's not a real word. Anyway, so let's continue here. As you'll notice, we actually have two examples here. Let's get back to an example where we introduce new input. Let's assume we have x1 of 1 and x2 of 2. You can guess what is y. Y will be 3 because we know like x1 plus x2 is equal to 3. And let's assume that for some reason we have a model which predict 5, like a y predict with some random weight is giving us 5. So the error of that A example will be equal to 2 because it's 5 minus 3, which is the expected value. If you look at B, which assuming it had a x1 of 3 and a x2 of 4, ideally we'll have expected to be 7, but in this case it's not the case. It's giving you 5 again. You take prediction value, which is our YB here of 5, minus the value that we expect, which is 7, it's giving a minus 2. Because as I tell you, we will be having different example. If you add these two errors, instead of telling you like both of them were wrong, adding them actually is giving us a value of 0, which is quite confusing because we don't want the value to be 0 here. We need, when we add errors, it should be able to give us a bigger number because both numbers are failing. Even though they fail differently, one of them here in this case is predicting 5 instead of 3, so it kind of overshooting or going beyond our response. So we're expecting 3, but it's predicting 5, so it's missing like 2 numbers. But the B example is failing differently. We were expecting 7, it's predicting 5, so it's kind of, undershooting, if that word exists also. So basically, it was far away from 7. But unfortunately, because our error is so naive, subtracting y hat from y, we actually end up with 0, which is not a great behavior. So that where having a different way of measuring how bad we are become very relevant. So that's where people make reference of the loss function. So the loss function is a mathematical function that is kind of quantifying your error nicely or better in a better format. In this case, the loss function will convert that error in a non-negative value. So making sure that if it's non-negative, then it can't cancel each other. So if it's like just positive all the time, it will just add up upon each other, and that will be helpful for us to quantify how bad we are across a batch or a group of numbers. And in this case, our loss function is defined as y 1 over 2 of y hat minus y. You can recognize this is our initial error, but square, meaning that whatever sign that difference is giving us, it always will stay positive because the square of a negative number is a positive number. So if you take 2 power 2, you get 4. But if you get minus 2 power 2 is like minus 2 multiplied by minus 2, which giving us minus minus give plus, so you get 4. That where math become relevant here. And by applying that, you can see back to the example we had previously, if we end up now adding the loss of A and loss of B, we are not getting 0 anymore, we're getting 4. So that's the behavior that we want. Okay, if you have any question about this, please put it in the chat or join our group here. group me. How is it called again? Join our group here on Discord. You can take a screenshot. If you have a paper you wrote math, something is not adding up, ask us there. We'll have people answering you. I will also be there to be answering any of your question on this particular part. So let's continue here in applying this loss function. You remember we were able to compute our loss back there. It was giving us minus 1.37, but now applying the loss, we now get a bigger value. So it's telling us that for our initial prediction here, starting from random by guessing parameters W1, W2, and B, we end up with a loss function of 20. Okay, so this is telling us how wrong we are in really quantifying or predicting addition, giving our input 2 and 3. So across many examples, ideally, if you stare on this function for a minute. So in the best scenario, what we really want is for the W1 here, so this is what you see here, its value to be close to 1, for W2 value to be close to 1, and for B to be close to 0. Why? After training, this is what we want the model to discover, because we know that actually addition is just adding x1 plus x2. And for this equation to become x1 plus x2, we need to bring this one to 1, because every number multiplied by 1 is that number. So x1 multiplied by 1 here will be x1, and x2 multiplied by 1 will be x2, and here 0 will stay 0. So that will make sure that our y predict is actually exactly y. But again, with machine learning, we don't have exact value. This is what makes it different with traditional programming. And this is a subject that confuses a lot of people, especially people coming from traditional software engineer. It's because they're expecting AI to be deterministic. It's not. It's probabilistic. So you will not have 100% accuracy on a business use case. You will not have a model that is 99.9999 or even 100% in classifying dog versus cat. Most of the time, it will be 99%. It might be 90%. It might be 85%. Depending on your business appetite, you can decide which threshold makes more sense. But remember, we are estimating the value. We are not giving you the exact value. Okay, so after several input-output mapping, assuming we will learn how this happened, we get a value of 1.000012, which is kind of close to 1, and we get W2 of 0.997235, which is still close to 1, but on the downside, and we get a B of 0.01. Ideally, it will be like B of 0.00 something, but in this case, it's still close to 0, okay? So back to our initial example. So we have 2 and 3 by applying with our new W, that is again coming kind of from the sky, but we will find out how do we actually get to this number or close to this number automatically using math derivation. But here you can see that the value of our error is a little bit smaller. And again, when you look at the loss, it's actually telling us the full story that actually 5.0032, which is the response based on the new parameter, is actually very close to 5. So telling us that the model has actually learned, or the parameter of W are parameters that are minimizing our loss function. Again, for a reminder, our error was like this randomly, but after getting value close to the estimated value, it's smaller. And again, better scenario is here in this case where the loss was 20, but after applying the value that we have here, the value is now close to 0. As you can see, as many zeros that are there, just telling you it's a very small number. Now comes the important question. How did the model discover those parameters? How can we understand how the model moves from any random value? Remember, you don't need to start a specific place. You can start with whatever number. There's some property of those numbers, but don't worry about that. You need to start with some random number, and from those random numbers, get back to the numbers that are close to the output you want to teach this neural network to learn, okay? So this is the interesting part. I love this part. And again, this is where we'll touch a little bit of math, but again, as I told you in the beginning, I will not introduce any mathematical function that is not useful for this lesson. Everything that I will tell you here, and I will show you immediately how we apply it and why it is useful, okay? So let's spend a minute here and look at this animation. So from loss to learning, we have a loss function that is telling how big our mistake is. And this is where we introduce this notion of derivative. Oh my goodness, derivative. I remember back in school, for context, I did math and computer science. Actually, it was just pure math. But basically, I learned derivative without understanding where the derivative apply in real life. And when I got to know machine learning through my master's, I then realized, oh my goodness. So this is why derivative are useful in real life. This is not the only way. It applies in different, domain in different ways. But in this case, derivative are what is guiding the model on how you fix the value of your parameters. And we'll get to the details. So again, we know the real value is 5, but we started by minus 137. We know the error is minus 637, and our loss function is 20. Big, very big. We want to make it small. That is our goal. So think of W1, W2, and B like some turning parameter that you need to switch, but you are not manually switching it. Think about when I was preparing this lesson, I thought about like radio back then. My dad used to listen to the radio, and you will see him trying to get the frequency. It was not like a digital, it was like the odd one. So he had to find the frequency that had the channel he wanted to listen to. So that pretty much the idea that you can get here when you have this parameter. You need to actually tweak them so that it has value that is minimizing your loss. What I just said there in Word, this is exactly what the partial derivative of the loss with respect to W1. So basically, how much rate of change to the loss happen when I switch W1 with a certain value. So that's why you can see, and that's the same formula that applies to W2. The way you move W1 or W2 or B in a certain direction, you are getting immediate signal on how that is impacting your loss. And now that is one part of the equation, but the biggest formula here is that once you get that partial derivative, you need then to update your old weight. So initially, remember, we started with some value of W1. So we need to take your old W1 minus a learning rate. Think of this symbol here like a learning rate. So just like I will explain more about that. But basically, you multiply your partial derivative of L with respect to your parameter, in this case W1, to a certain value that is kind of telling us how much should that change matter. Okay? And the value then, after a while, that training will be changing W2 after seeing a lot of examples, such a way that it will get closer to the L that we expect to be close to 0, and W1, W2, and B will actually also be close to 1, 1, and 0 respectively. Okay? So this is a very intuitive demo, just to make sure that you understand what we're trying to achieve here. So this formula was introduced by Cauchy. This reminds me a name that I ate when I was in school. The formula of Cauchy-Schwarz. Because every time they were teaching that notion, I was failing that formula. Anyway, that's a memory from the past. But anyway, so the formula of Cauchy, that kind of the researcher, you can see the article here if you are math inclined, and you can read a little bit of French. Because I think he's a French guy. He published it under the title Méthode générale pour la résolution des systèmes d'équations simultanées. And as you can guess, I speak French. Maybe I give that away with my accent. But basically, that's where this whole formula was introduced. Like, how do you update the value of your parameter with respect to the change on that parameter using partial derivative? And the way it applies for us, we know W1 new will be the OW1 minus learning rate of the rate of change of W1 of the loss with respect to W1, and that's the same thing for W2 and B. So now the question here is, what the learning rate? The learning rate here, as I told you, I will touch about it. You can think of it as a small positive number that you decide in the beginning of your training. So this is not something that is learnable. You just decide it. Like I'm setting it, most of the time people set it small. So in this case, we'll just be setting it of 0.1. Basically just a coefficient that is scaling how much, the rate of change is relevant here. So let's recap. we know how do we update the value to get close to what we know already. And again, in real world, you will not know. You will not know what parameter you need to switch so that the dog can be categorized as dog, not as cat. So those are things that the system will learn by itself by seeing different set of images. But in this case, we know because it's addition, you know, 2 plus 3 is equal 5. So no thing to worry about there. We know that the value need to be 110 so that the function actually match the addition rule that we all know. Okay, so the only missing piece here is that we know the all W, we know learning rate, we set it at 0.1, but we don't know the partial derivative of L with respect to W1, the partial derivative of L with respect to W2, the partial derivative of L with respect to B. So those are the 3 missing or 3 unknown that we need to find. Then we have the whole solution to make our soup. Okay? So let's start just recalling what we know already. So we know x1 equal to 2, x2 equal to 3, y equal to 5. Our parameter w1 0.14, our parameter w2 is minus 0.47, b is equal minus 0.22, y equal w1 x1 plus w2 x2 plus b. By multiplying all of this, we end up with minus 147. So I will keep the output here. You can see this blue here is just keeping us honest by remembering the value that we know already, and we will be discovering the missing value, which is the partial derivative. Okay, we know all this calculation, we know the error, we know the loss, so we'll skip that and go straight away to the first mathematical reminder that I mentioned from the beginning of the video. The first reminder I want to share with you is the chain rule. So the chain rule is a mathematical or derivative formula that some of you might have learned it in high school or maybe in college. So the chain rule, the way you do this is that imagine that you have a function f, which is a function of g, and g, which is a function of u, but you want to compute the partial derivative of f with respect to u. So what will end up happening is that you need to compute the partial derivative of f with respect to g, because f is immediately a function of g, and then you will do a partial derivative of g with respect to u, because g is a function of u. So basically you do the chain rule, and you will see it more clearly as we apply it to our formula here for our first unknown, partial derivative of our loss that we know already with respect to w1. What is that formula? Because w1, remember, we know the formula of the loss. The loss is 1 over 2 e power 2. But how do we get w in this formula? We don't. It's not there. So basically we need to use the chain rule. So the partial derivative will become the partial derivative of L with respect to e, because L depends on e. But inside e, we have y hat and y. If we go with y, we know the value is a number, so we can't really get w1 from y. Remember, keep the big picture in mind. We want to get w1, so because the partial derivative is with respect to w1. So that's why we'll go with y hat. So that's why you will now have partial derivative of e with respect to y hat. And finally, because inside the y hat we do have now y, we found it. Then finally the chain rule will allow us now to do the partial derivative of y hat with respect to w1. So you can see in the example that I explained why the chain rule was all about, I did do just 2, but in this case chain rule can be applied for as long as you need. So in this case we applied it, we move from the loss to e, from e to y hat, and from y hat to w1. Stop for a quick story. Again here just to take a break, moment for you to take a cup of water. Every time I used to have like math classes, it was interesting to realize that the exercise you do at with the lecture in the blackboard, or even with colleague in group, is not as complicated than what you get for your exams or what you get for your assignment or something like that. So it sounds like when I introduced this chain, I just show you like how to compute it for 2 value, but in real life here we applied it for 3, like we did the chain rule 3 times. So just to tell you that you need to understand the intuition, not really remembering the formula. Okay, so the same thing applied to W2. You can follow the same line of thought I just shared, and the same thing applied to B. And Now given that we now have all the components that we need, we now need to compute all these components, because now we have some unknown. What is the partial derivative of L with respect to E, and partial derivative of E with respect to y hat, and partial derivative of y hat with respect to W1. So here is our second learning. The power rule. So the power rule is that when you have a partial derivative of a variable in a particular power, it basically that power multiplied by that variable in the power n minus 1. So partial derivative of u n with respect to u is actually n u at the power n minus 1. Okay. So another rule here, you can think of it as constant and sum rule. So basically, if you have a partial derivative of two things that are like in bracket or in parentheses or whatever, you can actually distribute the partial derivative to f plus the partial derivative of g with respect to u. Same thing apply if c is a constant, it can actually go out, so that we can only remain with partial derivative of u with respect to u. And again, a partial derivative of a variable with respect to itself is actually equal to 1. So which end up like this whole formula is actually equal to just the constant. And finally, the partial derivative of a variable with respect to a constant, the constant will go out because there's nothing here, the partial derivative will be 0, okay? Because like if you do derivative of x of u, but you get a constant here or maybe another variable x or t, this will always be 0, okay? Now let's apply all of this step by step. And again, it's a busy slide. We'll go step by step. If you have a question, join our Discord channel or write in the chat here, and we will get back to you. Someone or myself will be commenting there to get back to you, okay? So the partial derivative of the loss with respect to W1, we know loss with respect to E. We can apply this formula, okay? You remember this one about the power, because this is the definition of L. We know that this is E power 2. So basically this power can come down. This is what you see here. And because it is down, it will cancel each other. And this 2 minus 1 will become 1. So we end up like this. All guy here will only give us E. Okay? Partial derivative of L with respect to E is giving us E. Now remember why I told you it was a trick to have 1 over 2 as our loss is because it will help us in cancelling. Here we didn't need to have complicated thing to compute because these two will cancel each other and we just have a simple variable of E. And E, we know its value, it's here. It's just y hat minus y, which is equal to minus c, so there's no guess there. Okay? Let's look at the second component and trace it down. E with respect to y hat. So this is E, which is y hat minus y. Because we will apply this constant and sum rule, so we'll distribute the partial derivative, so it becomes a partial derivative of y hat with respect to y hat, and the partial derivative of y with respect to y hat, because this y hat is coming here and here, okay? Which will then, because this is a partial derivative of variable with respect to itself, as we learn here, this is giving us 1. So that's why this part will give 1. But this place is partial derivative of y with respect to y hat. So this can be seen as a constant because it's a different variable, so it will give us 0. So all these components will be equal to 1. Yay! The final block. Okay? The final block is the partial derivative of y hat with respect to W1. So in this case, we know the value of y hat. Again here, it's x1 w1 plus w2 x2 plus b, which we know the value. But by doing the partial derivative, we'll be applying that sum. So we'll distribute the partial derivative over every component here. That's why you see partial derivative of w1, w1, partial derivative of w1, w2, partial derivative of w1 and b. Because in this case, x1 is a constant, it can go out, similar to what we did here. And we will end up with partial derivative of w1 with respect to w1, which gives us 1, okay, because it's partial derivative by a variable by itself. Here w2 is not a function, w1 it becomes a constant, this becomes 0, this becomes 0. So we end up only with x1, because x1 times 1 plus x2 times 0, which becomes 0 plus 0, gives us x1. So at the end, all this component here, so the partial derivative of the loss with respect to W1 give us E times X1. We know the value of X1, 2. We know the value of E minus 6.37. Then we have a new variable here. Our partial derivative of L with respect to W1 is actually equal to minus 12. Yeah, 2 more to go. So not getting into the detail, I will skip through this, but it's the same reasoning. Some of the components we now switch. We now have E times X2. You can follow the same reasoning. If something is wrong, please comment. I might have missed something, but I think the computation are correct here. So we'll get the new our new friend here, our second unknown, which will give us minus 19. And finally, we apply the same rule for B, and we'll get the final answer, which gives us E, because it's just E times 1 times 1, but at the end will give us minus 6. So we now have everything we need to update our W. So we have all the components to get new value of W, to keep tweaking it, changing it, so that we get to the exact value without doing it manually. That's impressive, okay? Again, we apply this Cauchy rule that I mentioned previously. So the odd value was 0.14 minus our learning rate 0.1, which is fixed. And then we'll apply this minus 12, which is the value partial derivative with respect to W1. We do the same thing with W2. We do the same thing with B. As you will see, we have new value for W1, W2, and B. So just for context, these are the initial value. It was 0.1394, W2 minus 0.47, B minus 22, but the new value is 0.21. You can see the difference. The second value is 1.43, and the last value is 0.41. Do you notice something? We lost the minus. This one trend to go close to 0, and this one is getting close to 1. So going in the right direction. So we need to be doing this, and we'll get into that loop in a second. But before we continue, how does the computer know how to change this thing? The other thing is a nice illustration that I wanted to give you. Imagine that you are in the top of a hill. I don't know which. You went for hiking or something like that. And they close your eyes. It's a new hill. We've never been there. They close your eyes and they ask you, can you find your way downhill? Interesting problem. So one of the solutions is maybe trying to, put your toe out there, try to feel. If you feel like, it going downhill, that maybe your trail down the hill. You need to be careful. Don't just go to the wrong side. But basically the idea behind is that you can use, your toes or something like that as a blind hiker, someone hiking, to learn how do you go downhill and go down such that your error are minimized. So that is this formula of gradient descent. So that's something that we'll not touch in this lesson, but basically that's one of the formula that allow the system to know how do you update the value in what mechanism you use behind the scene to make sure that you are actually going downhill and reducing your value of W. Okay? So let's now talk about our training data. Now that we know how the AI learn, and we've demonstrated with one example how we could do a forward or one pass through the learning phase. Ideally, we'll need to have a lot of examples, so often 1,000, million, or whatever numbers make sense for your use case. But for this demo, I chose exactly just roughly 5 examples, which is not a great demo. Ideally, we have many of them, but because I wanted us to do it by hand, one by one, I've chosen an example that will make sure that this example will help us learn how does the training data affect the learning signal, okay? The first example is with having x1 and x2 0, 0, and our y, of course, 0 plus 0 is equal to 0, and then we'll have 1 0, then we have 0 1, when we have 1 1, and then we have 2 3, and we've been working with 2 3 for a while now. But basically the reason I'm actually choosing this is because of 0 0 we are learning something is that we are freezing out x1 and x2. So because it's 0, everything multiplied by 0 will be 0. So that's why you see the power of the bias, because now we still want to learn 0, but the bias has freedom to change. So it can play around, and you will see how that is happening live as we'll be getting into the code. And in the second case is that we'll be zeroing out x2, but x1 will be 1. So both the bias and w1 will move, because remember w1 is multiplied by x1. The same thing applies for the example number 3, where we will be zeroing out x1, so w1 will always be 0 and will not change, and only w2 and the bias will change, okay? And then finally 1 and 1 both will change, and so on. We've seen in the case of 2 and 3, both are changed, and larger input actually scale the gradient, okay? But do not worry about that. Let's now get into a very important thing. That's why I told you it's very important to have big data, because your data need to fit in the model. So you can't just get any data. You need to have data that is actually helping you learn the underlying thing you want your model to learn, okay? So the way you can think about it in one slide is that when you are given a problem, you need to think about 3 things. Is my data allowing me to perfectly fit with the, is my model able to fit in this data? Basically, can I have a model that is generalizable such that if I see a new example, it will predict? So this is the fitting part. Or is my model underfitting, which means it's a simple model that is not enough capable to understand the complexity of the data, okay? So that's the case of multiplication. With this our one linear layout, that will not work. Or is our model overfitting? Overfitting is the case where the model just memorizes everything. Think about addition. The model doesn't really discover the function, it just memorize it. Like every time I will see 1 and 3, I will tell them it is 4. Every time I 2 and 3, I'll give it a 5. A model that memorized, guess what? The next time you ask it, what is minus 1, minus 3, it lost, because it didn't memorize that. But if the model learned, it fit, it can guess, and often the guess is close to the real answer, okay? Great. Finally, let's initialize this model we've been talking about. Yeah, the fun part, initializing the model. How do we define the model? If you're familiar with Python, we want to set a random seed, because we are setting this starting randomly. We don't want to change every time, so I just set it at 42. If you're not familiar with Python, forget about this. And we define a class, Python addition neural network. It can have any name. The way the class is that you have a init, which is like when you call this class, the thing that you initialize, we will have a random number, random uniform, which is give us a number that is random. So that's why we get that 0 minus 14. We do the same thing for W1, W2, and B. And then we define a function. You know, our x1, x2 is 2 and 3. And we want our prediction to be rounded and 2. So, but we are applying model.forward. So that's where we introduce this forward function, which is applying our formula exactly the way we've been talking about it. W1 plus x1, W2 plus x2 plus b. So there is no hidden code here. Our y predict is just applying the formula, okay? Great. Let's see how this works. Let's start with training the model. You have found the model. It's actually just defining our mathematical function in code. So nothing crazy. Let's train this guy. You will often hear notion about epoch, learning rate, train loss, step function. All of this is just like how let me define epoch. Epoch is given the total size of your data, how many times did the parameter see that data. So if you have a training set, in our case we just have 5 examples. If I see the 5 example all, and the second time I come, this is my second epoch, because the first epoch is the first time I went through the full data. So in our case, we will look at the 5 example 8 times. So which means that we'll have 40 steps. So this is where the step function is all about. The step function is how many times you have actually go through every single example. Example is every numbers in your training data or every instance of your training data. So recap, epoch is how much you've seen all the data. A step is every time you've looked at one item or one sample in your data. So let's go. We have x1, x2, we have y before we get our weight. So let's put everything together here for you. We are epoch 1, we have x1, x2, which is equal to 0, 0, 0. And we have our weight. Remember, we have 0.14 because back then it was rounded at 14, but it's the same thing here, the same weight we started randomly, and that's why we set the seed. And we know our y hat was equal to 0.22, actually 23, because in this case our x1 is actually 0, 0. So initially you saw me pausing there because I remember our x1 was 2 and 3, but in this case it's 0 and 0. So okay, so let's continue. We know our error will be basically y hat minus y because our y is 0, so error is actually the same with y hat, and our loss function will be 0.0253. Okay, so the partial derivative of L with respect to y hat we've computed in the past, you know, the formula, which was giving us just y hat minus y because the response there was like just the error E, which is equal to y hat minus y. And the partial derivative of the loss with respect to W1 is actually E times x1, which giving us is here 0 because remember x1 in this case is 0. Okay, we continue. Partial derivative of y with respect to W2 giving us 0 because it is E times x2, remember from the calculation we did previously. And here you see the partial derivative of the loss with respect to the B, the bias, is now giving us minus 0.22. So this one is not 0 because this is the importance of the bias. Even if x1 and x2 cancel out, B still gives us a learning signal. So let's see how does this update our W. So this is the plot that is helpful for us here. I'll put it on the left. Sorry if it is hiding previous math. But basically you can see the initial value we started with, nothing is changing, but B is changing. It was initially minus 0.22, but now it's minus 0.20 because even if x1, x2 were 0, 0, as you can see in the sample here, but the bias has learned from that contribution. Okay, let's go to step 2. Now in this case we have x1 equal to 1. Let me pull this up, and x2 equal to 0. Okay, and we want the response equal to 1. Okay, let's do that. We will continue. We have x1, x2, we have the W. What happened here? We compute all the formula. We know the error will be equal to minus 0.6, the loss will be equal to minus 6, and then the partial derivative will become minus 0.60. You can see it here because x1 is not 0 this time, so you will see that we'll get minus 0.0630. This is from the previous run, some of this, but the x2 will stay 0. Why? Because our x2 is 0 in this sample. Remember, our x2 is 0, and the partial derivative of the bias will also change to minus 0.06. Okay, so we update all of these guys. If you look at this, x1 has moved now, x2 has not moved because the sample was 1 and 0. In the next step, step 3, as you can see here now, in step 3, the x2 become 1 and x1 is equal to 0. So this is our third example. We will go through the same one. I will skip that quickly here and go toward the end. You will see now that x1 is frozen and x2 has moved. So basically, we are updating the weight. As you can see, this one is getting to 0. This one is trying to rise close to 1. And this one is actually kind of getting close to 0, but we're still learning. We're still step 3. And remember, we need 8 epoch and 40 steps. So I will speed this up. It will go quickly also from your side, but we will keep learning step 4, step 6, step 7. So all the math are happening behind the scene. As you can see, I'm not changing anything. I'm just pushing my forward arrow. We're at 12 now. We keep updating. What do you notice? X W1 is getting really close to 1. W2 is also getting really close to 1. We are 92 now. B is struggling, but as you can see, as we keep going, the updates are happening, the mathematics is going, we are tuning, we are finding the channel, we are finding the parameter, and B will start getting close to 0. Epoch 6. How do you decide the epoch? How do you start the step? Those are empirical things, so you need to play around with that. You start with epoch 5, you see how the model doing, you change it and things like that. Same with a learning rate, that LR component, you keep adjusting. As you can see, B now is getting close. We are in 36 epoch. The 6th step, close to the final epoch here. You can see we now have 0.068 for B. So really, really getting close. And 39, so we're toward the end. And finally, step 40. Yeah, we finish at step 40. We get a 1.00. You can see we're close to 1 with W1. W2 also close to 1. And B, we close to 0. After learning this parameter, so truncating it into value, our learn parameter that we did together, we trained this neural network with you. I didn't do anything behind the scene. I didn't use any package or any import anything. This is pure Python code that we ran together. If you're interested in this Python code, write to me in the comment. I can share with you the link on how you can play around with this beyond my presentation here. Or write to me also in our Discord community. I can get back to you on that. But basically, like the target should have been perfectly 1, 1, 0, but our learning process, just with 5 examples, seen 8 times, we're able to get close to those values, okay? So let's try it with some test case. Test cases are those numbers that we take randomly, and for fun here, we'll introduce a -2 to see did really this thing learn beyond the example that we've seen it, we've taught it with, okay? With 1 and 2, we expect it to be 3. Let's see how the model is doing. So we give it 1 and 2. It will go through the forward. It has the W1, W2 that we computed, not the random anymore. Okay. So our y hat, by applying the formula that we all now familiar with, will give us 3.0.3. So you see, we close. So instead of getting 3, we got a 3.61. So our absolute error, our E, is 0.03. And if you get our loss function, will be a little bit smaller too. So if you try a different example, a bigger one, this 10 and 20, you apply the forward, same stuff. I will skip through this. You can see the output is 29, even though the answer is 30. Again, just to remind you, we are estimating, we are not getting the deterministic answer. So our Y real or prediction is 30, but we got 29. Our error is 0.30. So not bad. Not bad. Finally, with -2 and 5, we go through the forward. We know our W. We get an answer of 2.94, but the real answer is 3, so still close of 0.05. So that close if you want to look it as a table, so you can see for all these 3 examples, this is the prediction our model did with the parameter that we've learned, which is quite close with the prediction, the real prediction for this value. So we were able to make the computer discover addition. Okay, so let's conclude. With modern AI, if you think about ChatGPT, Anthropic, OpenAI, they have bigger parameters. So ideally, what we did with you today, we just have like 2 parameters, W1, W2, and B. If you want to translate that to ChatGPT, like it will be something similar to this. This is small, but many parameters. So you have like this small component that mixed to other component, mixed that other component. So it's like a inside someone's brain, there's like many neurons connecting to each other. Again, this is the dream, mimicking the human brain or something similar. So you can think now that you know the math behind it, so it's the same trick, but it's a little bit bigger, a bigger mountain, a bigger math, and everything happened behind the scene is exactly the same thing. Okay? Here's our takeaway. Classical code, you write the rules. But for machine learning, you learn the rules. That is the difference. And you've learned through this simple example. How do you learn the rule? The AI today is doing the same thing, applying this mathematics behind the scene to really learn the rules to chat with you and to respond to your queries. So learning is measured with error and plus repeated correction. So the computer is getting corrected several times so that it learns to answer the question correctly. That's all for today, folks. I hope you like this. The next lesson will probably, the next time we'll be touching upon addition to show you something that is not as trivial as this. If you're interested, let us know if you like this content. I will touch on in the future on things related to how does the computer see. So these are the computer vision side of things. How does the computer talk? This is the speech recognition, which is actually one of my favorite area. And I have background in publication in this domain, but also natural language processing. How do computer understand your text, which is actually my area of expertise. But yeah, looking forward to your feedback. Send me a text, send me a message from my WhatsApp channel. If you're on WhatsApp, follow my channel, Dr. Kabongo, and I should be able to send some notebook there, some study materials, and also a reminder if I post any new things. If YouTube doesn't notify you, I can also send it through the channel for you to see. So you can see this QR code, scan them, join our Slack channel, join our Discord server, comment in the video. Please subscribe and comment so that you don't miss our video, but also helping us grow this community. But also join our WhatsApp channel here for more updates. Okay, I hope you like this. Have a great rest of your day. See you next time.